Picture a beam of plasma punching through a galaxy at nearly the speed of light. It travels for millions of years, carving out a glowing lobe of radio-bright material that stretches for a distance larger than the galaxy itself. And then, one day, it just stops. No explosion, no warning sign visible to the naked eye. The engine at the center simply goes quiet. For decades, astronomers have had a good idea of how these jets turn on. What they have never really understood is what happens in the moments after they turn off. A new study published this year in the monthly notices of the Royal Astronomical Society just gave us the clearest look yet. And the answer is stranger and much faster than anyone expected. Let's start with what these objects actually are. At the heart of many large galaxies sits a supermassive black hole, sometimes millions or billions of times the mass of the Sun. When that black hole is actively feeding on surrounding gas and dust, it doesn't just grow quietly. A fraction of that infalling material gets redirected into two narrow jets blasted outward from the poles at close to light speed. Where those jets slam into the surrounding intergalactic gas, they inflate enormous bubbles of magnetized plasma called radio lobes. These lobes can span millions of light years, dwarfing the galaxy that created them by a staggering margin. This entire structure, jets included, is called a radio galaxy. It's one of the most powerful phenomena in the universe, and it's also one of the loudest, at least in radio wavelengths invisible to human eyes. But black holes don't feed forever. Eventually, the reservoir of infalling gas runs low, or gets disrupted, or gets used up. The jets shut off. And when that happens, the galaxy enters its final chapter as what astronomers call a remnant radio galaxy. The lobes are still there, drifting through space, but nothing is refueling them anymore. Without fresh particles streaming in from the jets, the existing plasma slowly loses energy and fades from view. Here's the problem. Actually catching a galaxy in this fading phase is difficult. The lobes are faint. They don't have the sharp, energetic glow of an active jet, which means for a long time, remnant radio galaxies were more of a theoretical stage than something astronomers had studied in any real numbers. That changed with a research team from the University of Cape Town and the Inter-University Institute for Data-Intensive Astronomy in South Africa. They went looking for these fading giants in a specific patch of sky that had already been mapped in extraordinary detail by the XMM-Newton X-ray Observatory, because that region had years of accumulated data across multiple instruments. It gave the team an ideal hunting ground. They combined observations from the MeerKAT radio telescope, an array of 64 dishes spread across the northern Cape Desert in South Africa, with data from the upgraded giant Metrowave radio telescope in India, the LOFAR network based in the Netherlands, and the Jansky Very Large Array in the United States. 4 separate instruments, 4 separate datasets, all pointed at the same slice of sky. Out of that search, they identified 14 candidate remnant radio galaxies. But identifying a candidate is only step 1. The real test came next, to confirm whether a radio lobe is actually fading and not just naturally dim. astronomers use something called spectral aging. When jet particles are actively being fed by a black hole, they emit radio waves across a wide range of frequencies, with roughly equal strength across that range. But once the jet shuts off, the highest energy particles lose their energy fastest. Over time, the radio emission at high frequencies drops away first, while lower frequencies persist a little longer. By carefully measuring how the spectrum tilts, researchers can estimate not just whether a jet has switched off, but roughly how long ago it happened. Applying that method to all 14 candidates, the team confirmed that 12 were genuine remnants. Their jets truly had gone silent. The other 2 turned out to still be active, just faint enough to have looked deceptively quiet at first glance. Now, here's where it gets genuinely surprising. When the researchers calculated how long each of the 12 confirmed remnants had been fading, the ages came out far younger than expected. The shortest was around 8 million years. The longest was around 42 million years. The average sat at roughly 12 million years. To put that in perspective, previous studies of remnant radio galaxies had generally found much older fade ages, often tens of millions of years longer. This new sample was systematically younger across the board, and in a universe where structures form and evolve over billions of years, that difference is not a rounding error. It's a signal. What could explain it? One strong possibility is that astronomers have simply been missing an entire population of short-lived remnants. If a fading radio galaxy only stays detectable for a relatively brief window before its lobes become too faint to see at all, then previous surveys built around less sensitive instruments would have systematically overlooked the youngest examples. Only with tools as sharp as MeerKAT and the LOFAR network could this fainter, faster fading population finally come into focus. In other words, the picture we had of how radio galaxies die may have been biased from the start, not because the physics was wrong, but because we simply couldn't see enough of the evidence. There was a second finding buried in the data that's just as important. The 12 remnants weren't all at the same stage of decline. Some had jets that appeared to have switched off only recently, their lobes still relatively bright and well-defined. Others were far more evolved, their structures diffused and faded, having powered down long before. Rather than a single, uniform dying phase, the data revealed a spectrum of decay, a continuous timeline stretching from freshly extinguished to nearly gone. That matters because it tells researchers this isn't a single, predictable off switch. It's closer to a dimmer, one that some galaxies turn down slowly and others let fade in a comparative hurry. So why does any of this matter? Beyond the technical detail, because radio jets aren't just a visual spectacle. They're one of the primary mechanisms by which a supermassive black hole influences the galaxy around it, a process astronomers call feedback. Jets can heat surrounding gas, preventing it from cooling and collapsing into new stars. They can push material out of the galaxy entirely. In extreme cases, they can regulate whether a galaxy keeps forming stars at all, or shuts down into a quiet, aging structure. If black hole jets flicker on and off more rapidly and more often than previously assumed, that changes how astronomers modeled this feedback process across cosmic time. It's not a slow, occasional event. It may be a far more dynamic cycle of ignition and shutdown, repeating on timescales short enough to matter for galaxy evolution models built to explain how the universe's largest structures came to look the way they do. There's also a broader mystery this research doesn't fully answer yet. What actually triggers a supermassive black hole to stop feeding in the first place? Is it a sudden depletion of nearby gas? A disruption caused by a galactic merger? Some internal instability in the accretion process itself? The new data pins down how quickly a jet fades once it switches off, but the exact mechanism behind that first moment of silence remains an open question, one the same research groups are now hoping to chase down using even wider survey areas. For now, what we're left with is a more honest and more dynamic picture of a black hole's life cycle. Not a simple story of an engine that turns on, runs for a long time, and eventually dies. Instead, a more turbulent rhythm of ignition, feeding, shutdown, and fading, playing out across timescales that, on a galactic clock, are almost shockingly brief. Somewhere out there, right now, a jet that has been blasting across intergalactic space for millions of years is quietly winding down, its lobes beginning to dim in wavelengths no human eye will ever see, and thanks to instruments sensitive enough to catch that fade in progress, we're finally starting to understand what that ending actually looks like. Beyond what you can see, but never beyond what you can understand. Subscribe, and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.